Now, are you able to see the screen that I share?
Yes,
Yes,
sir.
sir.
Okay, so the topic today, okay, a quick recap of what we have learned last week. So we have learned on the, well, we introduced the forces that acting on the immersed body, which is a body surrounded by fluid moving at certain velocity, which consists of drag and lift forces, and drag forces and the lift force consists, actually you can break down them into the pressures in this drag, and also the friction in this drag, also the pressures in the sleeve and the friction. So two things, uh, pressure force, or sometimes call it also body force, and friction due to the shear stress, due to the viscous effect of the fluid in the vicinity of the wall. That's also bring us to the concept of boundary layers, dealing with the frictions of the plate layers nearby the wall. And then we actually discuss the laminar boundary layer, how we solve that. I mean, we cannot solve the overall flow velocity profile all the way from the wall to the infinity. But what we can do, actually, we can divide them into two major regions. First is when you have the boundary layer regions, and then the remaining is we can consider as an inviscid or non-viscous flow, because above that, where the velocity is close to the free stream velocity, we can consider the viscous effect is negligible. So we can use like the Bernoulli and so on. But on the boundary layer, the opposite, we should treat them differently, because now we have a viscous effect dominance compared to the inertia effects. So that's why we try to solve that. For example, last year's solution is one of them. The momentum integral equation is also the other one. So the point is, you want to have a velocity profile that you can relate into the shear stress, and then finally you can relate to the frictions, and then the drag associated with it, and also the lift associated with it. Okay, so we did that for flat plate, for cylinder or sphere. Okay, now we going to a little bit up with the drag and lift forces. How do we calculate them in practice? Because what we did for Blasius is really only apply for laminar flow, for example, and then it's also applied for a certain Reynolds number and so on. But the applications is um, showing more variation. So that's why it's going to be a lot of empirical equations, but you have the basic. So the drag and lift forces consists of two major contributions from the pressures, forces, and from the frictions. Okay, so I think this will give you, let me see. Yeah, we have this video before on the aerodynamic style of the airfoil. See if it's playing. Okay, I don't think it's playing. Okay, good. So as you can see, this is the air velocity plotting. The higher is the bigger the velocity. So, and this is the angle of attack when you try to have it. As you can see over here, you have high velocity over here, mean low pressures. You have also a little bit over here, and then you have low velocity, so that you're going to have a lift of this. But you're also going to have drag due to the profile and drag due to the frictions on the wall. And you can notice that there's actually what we call a separations, where the fluid layer detached from the profile. Over here, you can see they're still attached, but now it's becoming detached more and more upstream. When you have detachment, then you have turbulence over here. If you take a look on the air pressures, that will contribute mostly on the lift. You see, this is the right one is at the high pressures. So when you have this, you have more and more lift. The blue one is the lower one. Since pressure at the bottom is bigger, so it's going to create lift. The more angle of attack, the more lift you have until you have the stall. They call it stall, where you actually cancel the lift because of the shape on it. Okay, that's one of the applications on this one. So if we try to analyze what caused the drag, you have a profile drag or an induced drag. So the induced drag over here is dependent due to the vortex formation, span volume, lifting surface, and etc. The profile drag is due to the skin friction drag. It's, for example, because of the surface area, shear stress, the velocity gradient. That's actually what we are many of the this is regarding the boundary layer, and also the form drag. This is because the pressure distribution, volume shape. So this is the component of the pressure difference, and this is due to the frictions. There's also another one, wave drag, which is in our case is not really discussed. It's because of the gravitational wave phenomena, compressible flow, which is happens for air when you have a high velocity on this one. Okay, so if we take the component, we're going to take only two, skin friction and form drag, on our discussion here. So this is the form drag, cause of the pressure distributions. And this is the friction drag, caused by the frictions at the wall. And they are combined into the drag force. And then since it's difficult to determine the pressure distributions and also the shear stress distribution, we sum them up and then obtain CD, the drag coefficient, which sum up all the parameter affecting the drag of the of the body. So for example, the effect of Reynolds number, the effect of Mach number, Proud number, and relative roughness of the surface. So Reynolds number ratio, viscous and inertia and viscous. Mach numbers is the velocity divided by the velocity of sound. So that's reflect the velocity effect. And also the Proud number, when you have a free surface, it means like the body is at the interface between two free surfaces. For example, a boat floating where you have water and air. So they have free surface over there. So the Proud number affecting on that also. The relative roughness, E over L, E is the surface roughness average, is the length of it. So they all sum up together, and then usually we obtain that from the experiment. One example of the relations for the flat plate is presented here. So if you want to find the drag, for example, for this case, then you can just find what's your CD, the friction. Oh yeah, this is the drag due to the frictions. Okay, drag due to the frictions. For laminar flow, or transitional turbulent, and for example, completely turbulent. So we need to determine first what's the Reynolds number of the flow itself in order to be able to select which um, drag friction drag coefficient that we can use. So this actually one component of the drag, where the effect of this TW times the TA like that. So, but here we ignore the pressure distribution, the pressure distribution, or there is no pressure gradient in our case. Okay, and then the drag due to the pressure in this case, we can also get it from the parameter, which is the Reynolds number and the surface roughness. So from this equation, since we don't know the pressure distribution, we can sum up into CDP actually, this one CDP, not only CP but CDP. So drag coefficient due to the pressure difference. As you can see on the airfoil example here on the previous video, you have drag. For example, if you have separation over here, you have turbulence over here. Let me go from here. Then you have, this is P or P0, depending on which one is greater. And this delta P between the front and the back will create drag also, as well as the friction. But for the drag due to this pressure distributions, you can see where P minus P0. That's what caused the body to be dragged. Empirical result can be also used here. This CD is actually CD. This one for the ellipse, okay? For the ellipse over here, that has this shape, and then you have the velocity on this side. And then you can find the CD, and this is L over D. So the major axis of the ellipse, D is the length of the ellipse bar, for example. And you're going to have a difference between the frontal area or the planform area. This one is for the, if you have B times D over here, this is B times L over here. B is the length of this. So the difference between if you have the flow like this or like this. So you can find the drag coefficient from this one. So this actually gives you the effect of the shape into your drag coefficient and finally into your drag force. So you're going to have different. Another example of a major illustrations of the difference due to the shape dependence, you can see over here. You have a 10 diameter, and this is 1 diameter over here. They can have the same drag force due to circular. This is if you have circular cylinder, the CD is 1.2. But if you have streamlined strut, the CD is 0.12. So they can have the same drag force, although you have a different diameters by 1/10, for example. So that is actually caused by the prolonged attachment. So you delay the separations. So instead of you have separations over here, which will cause pressure drag. Remember pressure drag because of the different pressure in front and the behind or upstream and the downstream. But over here, you're going to have less pressure drag. So you end up finally, you may have the same drag force for both shape, even though they have a very different diameter or size. So yes, shapes determine the drag force also. So this table gives you drag coefficient for different shape. Okay, you're able to use it to solve, for example, for different shape. Apply for real number greater than 1000. This is specifically for airfoil. So there is an institutions or this is National Advisory Committee for Aeronautics, NACA. So NACA is publishing airfoil geometry guidance and then associated drag coefficient, because they have so many applications, the airfoil. So they did extensive experiments, and then they named, for example, NACA 0015 or NACA 662015. Those are the name of some of the airfoil profile. And then they plot the drag coefficient for this particular airfoil shape. So when you design an airfoil, for example, for airplane or even for wind turbine, for example, then you can use one of the NACA profile, and then they have the drag coefficient associated with the shape. Also, since in practice, you cannot change the shape while it's being used or while it's flowing. What you can do is you can modify the orientation. So shape and orientation is important. For example, in our case, like we did also on the video previously, we changed the orientations of the airfoil relative to the velocity directions. So the shape remained the same, but the orientation changed. And that caused the drag to change. Like this. So if you change the angle of attack, then you will have, as you can see over here, you may have a relatively constant drag, but suddenly around 6 degree, you're going to have like a lot of drag. So this section is due to the pressure drag. As you increase the angle of attack, now you're going to have like a big pressure different from here and from here, which will cause the drag of the airfoil. Over here is dominated by the friction drag. But once you get stall, then you have a pressure induced drag, which will cause you, on the next one is you will lose your lift force, because the lift force becomes the drag force at this regions. Okay. Again, shape dependence for several shape. So basically, what you have learned from this one is then you're able to get any shape, and then you can find what's the appropriate drag coefficients, and then you multiply with the half rho u square times the area, then you will get your drag force associated with the shape. Okay. Any question until this point? Okay, let's continue. So another parameter that is important for the drag is the Reynolds number, as we can assume, because that's reflections of the viscous effect on the flow. So you can divide into very low Reynolds number, moderate Reynolds number flow, or very large Reynolds number flow. So for very low Reynolds number, for example, Reynolds number less than 1, the drag is a function of the velocity, the length, characteristic length, and the viscosity. Okay. So if we do dimensional analysis, so this is dealing with the effect of the Reynolds number into the drag. Okay. So if we try to simplify this, where the drag force is a constant because it's a function of mu L times U times a constant C, we can say that CD is 2C divided by Reynolds number, where C is a constant. So it's only a function of Reynolds number for the low Reynolds number over here. Okay, for the moderate Reynolds number, CD is half to square root of Reynolds number for the moderate one. It is summarized on the following table for different shape and for low Reynolds number. For example, the CD for circular disc over here is 20.4 divided by the Reynolds number, and 13.6 divided by Reynolds number, and so on. Or for the spare, it's 24 Reynolds number. Hemisphere 22.2 over Reynolds number. So this is for low Reynolds number. Okay, this figure shows you the characteristic of the drag coefficient as a function of Reynolds number, and apply for smooth circular cylinder and smooth sphere. So this is the smooth cylinder, the dot point, and this is the smooth sphere, the continuous line. Smooth sphere and smooth cylinder over here. And this is the Reynolds number. So the higher the Reynolds number, the lower the drag coefficient, because the viscosity effect is less important on this one. So the turbulent boundary layer travels further along the surface into the adverse pressure gradient on the rear portion of the cylinder before separation occurs. And this results a thinner wake, small pressure drag, and sudden decrease in CD, in the drag coefficient. So if you have, so there is a certain Reynolds number that will cause the drag drop sharply and then increase back again after that. So if we analyze further this phenomenon, we can take a look on this one just to give you some idea what's going on. This is the same graph on like the previous one. What's going on this particular point over here? So when you have no separations, low Reynolds number like this, you have the drag. So and then you start increasing the Reynolds number, and you start having turbulence over here. But the drag is become smaller, and then on C you have this one turbulent more and more. You have also this becomes smaller because this there is a oscillating Kalman vortex. It's a kind of turbulent also. And then on part D, you have increasing Reynolds number become turbulent, and then on E, where you have this sudden decrease of CD, you have this delayed separations. So as you can see, this start over here, but now it start a little bit further back. That caused the decrease of the drag. You have a thinner wake, and then you have a small pressure drag and sudden decrease in the drag coefficients. So this is the phenomenon occur for the flow of a cylinder and sphere. They have a similar phenomenon on that. This gives you for different shape before for the cylinder and sphere. This gives you for in here for the flat plate, circle, ellipse, and so on, and airfoil over here, and so on. So yeah, so you can have this, and all of them have a little bit change on the drag coefficient and subsequent drag force on a certain Reynolds number, especially when the Reynolds number start to become turbulent. So oh yeah, and there is a term called the streamline and the blunt bodies or the block bodies, like this blunt bodies, or the also the called bluff bodies. Yeah. The drag coefficient decrease when the boundary layer becomes turbulent. But the pressure drag decrease, but friction drag increase because of the drag. So streamline is when you have the shape minimize the pressure induced drag. When you have dP is lower, then you have a streamline. When you have dP is high, you have blunt body. Or easily you can assume that, or you can say that blunt body is like trying to overcome the flow direction, while the streamline is on the flow direction. So for example, this is a blunt body, but this one is streamlined body. So it depends on the orientation also, of course. For blunt bodies, the drag coefficient decrease when the boundary layer becomes turbulent. So the change is when you have this change of the flow characteristics from laminar to turbulent. Remember, laminar to turbulent, of course, transition is 5 times 10 to the power of 5. So once you reach that, you have decreasing. Well, actually, this is decreasing the pressure induced the drag, yeah, because of the turbulent, the pressure. So remember the before CdP. So the pressure induced drag decrease, but you have another component of CdF, the frictions, and drag is the combination of those two components. This one. So for blunt bodies, the drag coefficient decrease when the boundary layer becomes turbulent is due to pressure drag decrease, although the friction drag increase, but the total of them still decrease because they contribute on different level of magnitude. While for the streamlined bodies, the drag coefficient increase when the boundary layer becomes turbulent. It's not because of the pressure drag, it's because the friction drag. So they are competing each other on contributing into the CDF, yeah, and CDP, and those combinations should be plus because they have the same, but they're contributing each other, so they're superposition each other. Okay, any question until this point? So far we have, we have discussed the effect of the shape, the effect of the Reynolds numbers, and next is the effect of the surface roughness. We still discuss about the drag, but what's the surface roughness dealing has things to do with the drag? It does. So the surface roughness also induce the drag. Not only the it's actually mostly because of the friction drag, and also this is interesting because you assume that if you have a rough surface, then you're going to have a high frictions. Intuitively, you will think of like that. That's true, but on the micro level, if you able to create a surface roughness that introduce turbulence, that will cause the pressure drag decrease. So you may have increasing frictions drag due to the surface roughness increase, but in a certain way you can have a pressure drag decrease because of that, and those combined effect may have a total decreasing drag force. So it's not always when you have a surface roughness that's going to decrease the drag, the total drag. It will obviously increase the friction drag, but in some way it also may decrease the pressure drag, so that the total drag become less. So the surface roughness protrudes through the laminar sublayer adjacent to the surface and alter the wall shear stress. Okay, then you have an increased turbulent shear stress. We're talking about the boundary layer, inside the boundary layer. Okay, And the surface roughness can alter the Reynolds number at which the boundary layer becomes turbulent. A rough flat plate may have a large portion of its length covered by a turbulent boundary layer than the corresponding smooth plate. Yeah, of course, because then you're going to have like more turbulent flow inside the boundary layer. For streamlined bodies, the drag increases with increasing surface roughness because turbulent shear stress is much greater than the laminar shear stress. Okay. But for extremely blunt body, such as a flat plate normal to the flow, it's like having like this plate, and you have the flow going into this one. The drag is independent of the surface roughness because of these small portions that so we can ignore the surface roughness for this form because the dp is more dominant, much more dominant than the df due to the frictions. For blunt bodies like a circular cylinder or sphere, an increase in surface roughness can actually cause a decrease in the drag. This is what I was talking about. So if an increase in the surface roughness, intuitively you will say that will increase the drag because of the friction. It's true for the friction, but the total one may decrease the drag because a considerable drop in pressure drag. Remember, the component is pressure and the friction. The friction may increase, but the pressure drag may decrease.
Sir,
Yeah, go ahead.
I have a question. In this case, for the blunt bodies, does it work like a ship hull or a shark, for example, that has like microfibrils on their surfaces to create to reduce the drag when they're moving?
Yeah, that's one of the example because it's mostly for the blunt bodies. It means like you cannot actually overcome the pressure drag, so that's why you modify the surface so you're able to have you have an because of the modification of the surface, you have a slight increase on the friction, but you have more decrease on the pressure drag, and that's one of the examples.
All right, understood. Thank you, sir.
Yeah, another example is the let's say the dimples on the golf ball. Um, the the um, the golf ball with dimples can go much further because it has less drag compared to a smooth golf ball, for example. We will go into
Oh,
that later. But that's one example of putting surface treatment to make it rough may increase the friction, but may decrease the pressure, pressure, the drag pressure. Sorry, the pressure drag, the drag force due to the pressures difference. Okay, and the underlying explanations to that is you have when you have a high surface roughness, rough surface, then you have a turbulence at the surface. Okay, and then they will delay the separation. They will delay the separation, and then they will, if you have more attachment to the flow, then you have the pressure drag decrease. I think I have some visualization on that. Okay, this one is this curve can give you. Okay, this one. So take a look on this red curve over here. So the red one is when you have a smooth ball, spare, for example, flowing with different Reynolds number. So the higher the Reynolds number, you have the slightly change on the drag, and then when you have when it's become turbulence, 5 times 10 to the power of 5, you have a decrease on the drag. Okay. Um, there is a way to modify this, because in order to reach this, you have to have high velocity. And then, for example, for the Golf one, or for the ship that you talked previously, it's hard to get into that velocity, right? So what you can do is actually you introduce surface roughness or dimples on the golf ball that will alter the characteristic of the drag force. This one, this one you have this the graph. Let's say let's use a blue color over here, like this, and then you're going to have the same one like this, for example. So there is a delta over here that you have a much lower drag coefficient, but at smaller Reynolds number. Means like you can still have less drag with less velocity, which is in the range of the speed of the golfer hit, for example. So this why, as you can see, this is pretty high decrease on the drag with less velocity. I mean, if you use the smooth ball, you need to reach this region to be able to have less drag. But with the surface roughness, you can reduce your drag even at the lower Reynolds number. And it's because there is a turbulence created at the boundary layer that delay the separations and then cause the decrease on the pressure drag. Okay, any questions? I think I can a little bit jump to this video.
Sir, can I ask a question?
Go ahead.
Uh, Kalau ditanya what is the drag on a surface, itu tuh berarti kita harus two equations ya, yang drag by pressure sama drag by friction ya. Terus kita tambah bukan?
Yeah, that's true. That's true. So some some reference actually give you separately for CDF and CDP. So drag due to friction and drag due to pressure. If that's the case, you have to sum up all together to get the drag coefficients. Okay, but some of the reference actually already join them together. That you just use the CD that given that include the pressure and the pressure drag and the friction drag. So for example, the previous graph, this already include both of them, the frictions and the pressure. Okay, does that answer your questions? Okay. Hmm. Okay, so that's the visualization of the gold flow and the error flow at the surface. So, and then that will reduce the pressure drag considerably and the total pressure and on the total drag over there. So any questions? I think we can do a example over here. If we have a golf ball with the known diameter and weight, and then it travel around 200 feet per second, and we have tennis balls for comparisons, um, and then we need to determine the drag on a standard golf ball, smooth golf ball, and a table tennis ball for the condition given. Okay, so for the drag force, we can have this. And I think everything is known. U, D is known except for CD. CD we can get it from the curve also. Um, let's go. Oh, first we need to calculate the Reynolds number because the curve over here depends on the Reynolds number. So you need to determine first what's the Reynolds number. So you have for the golf ball, 1.79 times 10 to the power of 5. Well, that's actually on the close to transition, but still in the laminar. For the table tennis ball, you have 4.78 times 10 to the power of 4. And for the, where's the other one? Okay, yeah, well, the same. Well, the golf ball, even though they're standard or smooth, they will still have the same Reynolds number for our case, for example. And then if we try to find what's the drag coefficient, remember this drag coefficient already combined the friction and the pressure drag. Okay, so if we take the previous one, 1.79 times 10 to the power of 5. So probably around this point. The question, if this is a smooth, means you have to follow this one. So you can go up, for example, and then find what's your, so this is for the smooth. For the, let's say if you have put dimples or non E over D, you can at the same this one, but now you have only until this point, and then you get the CD over there. this one over here. Well, you can just, which in our case, E over D is closer to this one. While for the tennis ball, CD the same. CD is it's a little bit over here, I believe, because the Reynolds number is smaller. Let's say somewhere over here. And since it's smooth, you can have this. So 0.5. So you have different drag coefficients for the standard golf ball with dimples, golf ball without a smooth golf ball, and then this is for the table tennis ball. As you can see, it's illustrated here. You have half actually the drag force compared to a smooth one. So that's illustrate the importance of the surface something. Yeah, so this is the calculation of the drag. Half rho u square times the area times the CD. And later on, when we discuss lift, this also going to produce lift. And it's due to the spin of the ball. So dimples or the surface roughness will reduce the drag and increase the lift, which we will learn later on. So that's why they can go further with same force given compared to the smooth one. Okay, any questions?
No, sir.
Okay,
No, sir.
now we going to the next topics, the lift. We can't separate drag and lift because for a body immersed in the fluid, then you can have, you will have both lift and drag. And then for the most applications, you want to have more lift and less drag. That's why, but we will have both of them. The streamlined bodies will have more lift and less drag, while the blunt body, you will have more drag than the lift. So the lift is defined as the component of the surface force exerted by a fluid on a body perpendicular to the fluid motion. So again, also the same like when we have a drag, it consists of the pressure component and the friction component. And also the same approach, in practice we use the lift coefficient to get the to simplify them. The lift coefficient itself is a functions almost the same, like when we discussed the drag. Shape, Reynolds number, Freud number, Mach number, and also the surface roughness. More or less the same, yeah. Okay. And yeah, most common lift generating device, for example, airfoils, fans, for example, turbine, spoiler, cars. It's operated in a large Reynolds numbers, so the flow will be turbulent, and then the viscous effect will be just on that boundary layers and the wake regions downstream. Okay, and most of the lift comes from the surface pressure distributions. And the wall shear stress contributes little to the lift. So this component previously, this is very small. And this one is dominating. And the relative importance of shear stress and pressure effect depends strongly on the Reynolds numbers. For very low Reynolds numbers, viscous effect are important, and the contribution of the shear stress to the lift may be as important as the of the pressure. But this is when in practice you may have this condition. For example, for a very viscous fluid, like uh, mud, okay, and you have a body moving through the uh, through the mud, okay, then your leaf is may the contribution of the shear stress or the frictions may be important to create the leaf. For example, if you have an object um, drop, okay, object drop through the mud, okay, the viscous effect may be important and create the lift to overcome the mass going down. Okay, so that's one example. I think we use that on the viscous method. Viscous method. So when you have a low Reynolds number, you can actually use that principle to calculate the viscosity of the fluid itself, because the viscosity become important. But for the most application on aerodynamics, where the viscosity of the air is very small, so the and also the usually for the aerodynamic it's operate as high Reynolds number, high velocity, high Reynolds number. So that means you're going to have uh, friction effect negligible compared to the uh, pressure effect to the leaf. Okay, we can use Bernoulli equation because viscous effect is neglected, or we can ignore that at a high Reynolds number, so it's become invisible. We can also say that location with high speed flow and low pressures have low pressures, and location with low speed flow have high pressure. Is Bernoulli equation: high pressure, low velocity, uh, low pressure, high velocity, and so on. So this is pressure distribution on the surface of an automobile. So this is high pressure, the black one. Oh yeah, I forgot to. High pressure, the black one, and then blue one is low pressure. Okay. And one device that is used to create lift is airfoil. This is to produce lift, and is generated by pressure distributions below or top and bottom of the surface. For large Reynolds number flow, this pressure distribution are directly proportional to the rho u square root 2. And then viscous effect is not really important. Symmetrical airfoil cannot produce lift because when you have symmetrical like this, then the pressure at the bottom and the top will be the same. So you won't have lift. So that's why you need to create non-symmetrical one with a certain angle of attack or orientation. So for this one, you can create lift because the air travel further, so you have high speed and then lower speed, and then you create high speed means low pressure, low speed means high pressure, and you create lift as the resultant. Okay, and then yeah, angle of attack. Angle of attack is determining the orientations relative to the stream flow velocity stream. Then you can have this is angle of attack, and the axis and the velocity over here. And we have also some of the chord length is straight line joining the leading edge and the trailing edge. So this is the chord length from the front to the back over here. And the aspect ratio is ratio of the square of the length of the airfoil. So B to the B square over BC. So B square over, oops,